Welcome to today's explainer. If you've ever really stared at an NMR spectrum, you already know that spectroscopy is, at its core, molecular detective work. It's about finding the clues. And today, we are going to learn how to read some incredibly specific structural fingerprints. We're talking about the traces left behind by heteronuclear coupling in carbon-13 NMR. So instead of just looking at your standard everyday carbon-proton interactions, we're focusing entirely on how carbon-13 interacts with three very distinct suspects: deuterium, fluorine-19, and phosphorus-31. So, here's our roadmap for today. We'll start with the basics of nuclear spin, then we'll look at deuterium, which acts as our solvent signature. After that, we'll examine fluorine-19, the giant splitter. Then we'll explore phosphorus-31 and the distance factor. And finally, we're going to bring it all together and crack the structural code. All right, let's dive right into section 1, the basics of nuclear spin and our foundational rules. Okay, so to really grasp coupling, we first have to wrap our heads around nuclear spin. Basically, any atomic nucleus that possesses either an odd mass, an odd atomic number, or both, is going to have a quantized spin angular momentum. Put simply, these nuclei behave exactly as if they were tiny little spinning tops, and because they carry a charge, this spinning creates a tiny readable magnetic moment. It's like a micromagnetic environment that our NMR spectrometer can actually detect and measure. Now, this table right here, it's basically the Rosetta Stone for our entire explainer. Pay special attention to the formula in that right column, 2i plus 1. The spin quantum number, which we call I, completely dictates the number of allowed spin states for a given nucleus. For carbon-13, fluorine-19, and phosphorus-31, I is simply 1/2. You plug that into 2i plus 1, and boom, you get exactly 2 allowed spin states. But look closely at deuterium down at the bottom. Its spin quantum number is exactly 1. That completely changes the math, and as you'll see, it totally alters the structural clues we're going to find on our spectra. Moving right along to section 2, deuterium solvent, our classic solvent masking agent. So we just saw that your standard hydrogen, the everyday proton, has a spin of 1/2. That gives it just 2 allowed spin states. But when we swap that out for its heavier isotope deuterium, I equals 1. So applying our 2i plus 1 rule, deuterium actually adopts 3 distinct, equally probable spin states, -1, 0, and +1. And this fundamentally changes how it splits the signal of an attached carbon atom. Which brings us to a really crucial point. In a standard NMR solvent, like chloroform D or CdCl3, the carbon atom is directly attached to a deuterium atom. Because those 3 spin states of deuterium are equally probable floating around in the solution, the carbon-13 signal gets split into 3 perfectly equal peaks. I mean, if you've ever run a spectrum and panicked for a second, wondering why your clean solvent singlet looks like a messy 3-line split, take a breath. It's not a mistake. That right there is the 1-1-1 triplet. It's a massive, predictable structural clue of carbon-deuterium coupling, and honestly, one of our prime suspects in the lab. And this brilliantly illustrates just how consistent these interactions are. That 1-1-1 triplet for CdCl3 has a very specific one-bond coupling constant of right around 45 Hz. It acts as a totally distinct, measurable fingerprint for a single bond between carbon and deuterium. You see 45 Hz, you know exactly what you're looking at. All right, on to section 3, fluorine-19 splitter. Get ready for some massive carbon impacts. Check out this spectrum for CFBr3. Notice anything? Even when the proton decoupler is completely turned on, the fluorine atom is still stubbornly coupling to the carbon-13. Why? Well, because fluorine-19 has a nuclear spin of 1/2, just like a standard proton. It follows the exact same n+1 rule we're used to. So with one attached fluorine atom, the carbon-13 signal is cleanly, beautifully split into a doublet. But wait, look at this number, 370 Hz. If we calculate the difference between the 2 peaks of that doublet we just looked at, we get a 370 Hz gap. I mean, wow, that is an absolutely giant one-bond coupling constant, especially when you compare it to typical proton couplings. When fluorine is directly attached to carbon, the splitting isn't just noticeable, it's absolutely massive. Now, let's see how this builds when we invite more atoms to the party. This is the carbon-13 spectrum of CF3CH2OH. Notice that massive quartet centering right around 125 ppm. Since we have 3 directly attached fluorine atoms, our trusty n+1 rule kicks in. 3 + 1 = 4, which gives us a quartet. Having multiple fluorine atoms scales the splitting pattern up spectacularly, and it maintains a huge one-bond coupling constant of 278 Hz. Moving into section 4, phosphorus-31,
distance and the space between atoms.
Okay, so here we have the spectrum for tetramethylphosphonium chloride. Just like fluorine, phosphorus 31 has a nuclear spin of 1/2. This means a single adjacent phosphorus atom is going to split the carbon-13 signal into a doublet. See this one-bond coupling sitting around 12 ppm? The phosphorus splits the carbon signal into a doublet separated by roughly 56.1 Hz. But this begs the question, what happens when the interacting atoms are a bit further apart? Well, we see this really cool phenomenon called distance decay. Literally, the physical space, the physical distance between atoms shrinks the coupling constant. It shrinks that Hertz gap. So a direct one-bond coupling, which we notate as 1J, is going to have a significantly larger Hertz gap than a two-bond coupling, notated as 2J. As the number of intervening bonds increases, the spacing drops dramatically. It's kind of like an echo fading out across a canyon. Let's look at this visually. On the left, our CFR3 spectrum shows that massive one-bond carbon-fluorine split we talked about. Now, on the right, back in our CF3CH2OH spectrum, look closely. There's another quartet hiding around 62 ppm. That signal comes from the carbon atom that is 2 bonds away from the fluorines. Because of distance decay, the coupling constant for that 2-bond interaction shrinks all the way down to about 35 Hz. So physical distance physically shrinks the spectral gap right before our eyes. All right, we made it to section 5, cracking the code. Time to synthesize our clues. So let's round up our suspects. Here are your core visual profiles. Deuterium? It has a spin of 1, instantly revealing itself as 111 equal triplets with about a 45 Hz one-bond gap. Fluorine-19, spin of 1/2, strictly follows N+1 rules but gives itself away with those giant, massive one-bond couplings, up to 370 Hz. And finally, phosphorus-31, also spin 1/2, perfectly demonstrates distance decay dropping from large one-bond gaps all the way down to tiny two-bond gaps of around 6 Hz. So as we wrap up this explainer, I want to leave you with a bit of a challenge. Think about this. How might you apply these specific splitting rules and distance decays to map out the structure of an entirely unknown molecule? Seriously, chew on that. With this toolkit, you can step into the lab and solve massive structural mysteries using only your carbon-13 spectrum. You might not even need to see the protons. Thanks so much for exploring the data with me today, and keep looking closely at those splits.